show at some point, you know, you are live. Yeah, here we go.
Yeah.
Got it. Perfect. I think we are live today for our last webinar of 2021. This is very exciting because we're going to reach next time the 20th webinars that we've been giving you. And we're really happy about this. This adventure has been fantastic. And I want to thank again my three co-creators, co-runners of these webinars, Ryota, Takunda, and Delphine, because it's been a great adventure so far. So today we have Michael. I should have asked Michael how to say his last name first. Michael?
It's Mikael Kaandorp.
Kaandorp, okay, Mikael Kaandorp. So we have Mikael today. He's going to talk to us about combining ocean models and observational data to create a 3D map of marine plastic pollution. And I guess this is kind of, you know, the graal of what everyone is looking at, and especially the people trying to monitor marine plastic everywhere. And Mikael is a PhD researcher at the Utrecht University in the Netherlands. As part of the tracking of plastic in our seas, TOPIOS project, of which our ocean plastic webinar friend is from as well, Delphine. His research focuses on how to combine large-scale ocean models with observational data to create a better understanding of the marine plastic mass budget. By using data-driven tools such as machine learning, the goal is to get a three-dimensional map of plastic in the ocean and to find out what is the most important source and what are the things. All right, Michael, if you want to share your screen, share your PowerPoint. I will just quickly remind our viewers that they can ask questions in Slido. So it's sli.do. The code is OPW, like the Ocean Plastic Webinars. And this information will be given throughout the talk by the slides of Mikael. So Mikael will give us about half an hour presentation here. And after that, I will read you guys your questions and I will ask them to Mikael. Don't forget that you can vote, give thumbs up to your favorite questions. So that's the ones I will be asking first, because I'm sure there will be plenty. I'm looking forward to this talk. And Mikael, the floor is yours.
All right. Thank you very much for the introduction, Audrey. I'm really excited to be here today to talk about the work that I've been doing for the past couple of years for my PhD research, which is trying to create this three-dimensional map of marine plastic pollution by combining ocean models and observational data. So this work that I'm doing together with my supervisors, of course, Henk Dijkstra and Erik van Sebia, and also the other co-workers listed here. So I'm sure that most people listening to these webinars are kind of familiar with the nature of plastic pollution. But just in case, I will give a short recap. So we have these gyres in the middle of the oceans where a lot of plastic particles accumulate. So as we see in this picture, in some of these regions, we have more than 1 million particles per square kilometer. So what we see is that we have two main gyres in the Northern Hemisphere, so in the Pacific and in the Atlantic. And in the Southern Hemisphere, we also have these gyres in the Atlantic, Pacific, and also the Indian Ocean, not pictured here. So in this study from 2015 by Erik van Sebia and co-workers, they calculated how much plastic there is in total in the surface water of the oceans. And there they get to the figure of about 240,000 metric tons, where a metric ton is 1,000 kilograms. This sounds like a lot, of course, until you compare it with estimates of what's entering the ocean every year. So also in 2015, there was this paper by Jambeck and co-workers, and they estimated that about 5 million metric tons of plastics enter the ocean every year. So the big question now is what is causing this discrepancy? Why is like 99% of this plastic missing, basically? And to dive deeper into this question, I first want to zoom in into the Netherlands, pictured here in this red box. And I want to start off with these two photos that I made. So last year I went to the North Atlantic garbage patch with a scientific cruise. And what we did here is we filtered some water using big nets. And after filtering about 1,000 square meters of water, this is what we find. So a lot of really small plastic fragments, some fishing lines as well. And then on the right, we see a picture I took on the beach on Texel in the Netherlands. And you see just on a couple of square meters, you can see some bottle caps lying around, some packaging for a drink. And also, if you look closely, you can see some fishing lines. So here is green one, here is orange one. So you could argue that at least in terms of mass, the plastic concentrations on the coastlines might be higher actually. So maybe this is one of the missing sinks. Maybe this is one of the areas where all this missing plastic is going. So that's what we wanted to investigate for the Netherlands in this case. So what we did is we teamed up with Stichting de Noordzee or the North Sea Foundation. And what they do is they organize this Boskalis beach cleanup tour every year. So between 2014 and 19, they organized these tours about 180 times. And a really nice thing about these tours, they kept track of how much litter was gathered. And they also know how many kilometers were walked. So from this, we get these basically these 180 observations, so the plastic concentrations that were found on the beach. And a really unique thing about this data set is the amount of participants, more than 14,000 actually, and also the amount of person hours going into this data set, more than 80,000 hours. And then the main questions we want to answer using this data set are, can we predict how much litter beaches on the Dutch coastlines? And what kind of conditions lead to the beaching of litter? So for example, what kind of weather conditions? Trying to predict how much litter beaches is actually a really complex problem because of the many physical processes near the coastline. So here in this picture, you can see what kind of physical processes play a role in the transport of marine litter near the coast. So we see all kinds of different currents. We see that waves break in this area. We have mixing of particles into the water column due to turbulence. We also have the fact that particles beach, but might also resuspend back into the ocean again. And we also have, for example, tides. So all these different processes make it really difficult to model this using a traditional physical model. So what we did instead is use a machine learning approach. So from these beach cleanup tours, we basically get these measurements of the plastic concentrations. And then we want to relate these plastic concentrations to certain explanatory variables. For example, the currents, the waves, the wind direction and magnitude, the coastal geometry and the tides. So basically, we want to know what kind of weather conditions, what kind of currents and waves lead to more plastic pollution on the beaches. Then we let an algorithm try to find a relation between these variables and the measurements. So basically, we want a map between X and Y. So this might sound kind of fancy, but I'm sure you're familiar with a really basic example of linear regression. So let's say in this case, the plastic concentrations, so the measurements we call Y. And maybe in this case, we have the wind speed on the x-axis, so that will be X. So we can take a lot of measurements. Those are the black dots in this case. And we try to find a relation. So in the case of linear regression, we just draw a straight line through the data, and we have two parameters. So we have a slope and an intercept. The approach that we use is not that much different, only we use a more complicated algorithm called a random forest. And this has a lot more parameters to tune just than a slope and an intercept. So what we want to do is we want to relate plastic concentrations to these kind of environmental variables. In total, we created a really large set of about 340 variables based on, for example, the tides, the currents, the winds, and the coastline geometry. So let's, as an example, take this beach over here, indicated by this cross. At this location and at the date of the measurement, we can look what was the wind speed, for example. But as you can imagine, the amount of litter that we find on the beach also depends on the previous days, so the days leading up to the measurement day. So that's also why we take into account different lead times for these different variables. And also, as you can imagine, these variables might also have a radius of influence. If you look at the transport of litter, we also want to know what are the currents further away from this measurement location. So that's also why we took into account different radii of influence. And finally, we also want to take into account directional information. So for this beach here, We calculated the orientation, which is this orange arrow, as you can see. Now we want to know, for example, are the currents pointing onshore or offshore? So in this case, the onshore currents would be indicated by the red arrows, and offshore components would be indicated by the blue arrows. So all this kind of information we want to feed to this machine learning algorithm, and all these different combinations lead to a total of 240 variables. Then we let the machine learning algorithm create a map basically from these variables to the observations that we have. So that's what we did. We trained this machine learning algorithm, and afterwards we were able to use it to make extrapolations from the entire Dutch North Sea coastline. And that's what you see in this picture over here. So in this picture, we see the mean litter concentrations along the entire Dutch North Sea coastline. So the concentrations vary from about 20 kilograms per kilometer to about 80 kilograms per kilometer. And if we sum up all these concentrations, we get about 16,000 to 30,000 kilograms of litter along the entire Dutch North Sea coastline. And also, if you look at this figure, you can see that we predict more litter on the mainland of the Netherlands compared to, for example, the south of the Netherlands. And we want to figure out what could be causing these differences. So what we did is we inspected the machine learning algorithm. So we inspected basically the map that we made. And there we found especially that tides play a really important role. So what we see is that a higher tide and more variability in the tide generally leads to less litter found on the beaches. So we think what happens is as the tide gets high, it likely recaptures a lot of the litter back into the ocean. And also we see that more exposed coastlines generally accumulate more litter. So that's, for example, the case in mainland. It's more exposed, so it's more directly located next to the North Sea compared to, for example, the south of the Netherlands. So this is called Zeeland, where we have more of these bays. So we think these two factors explain why there's less litter in the south of the Netherlands compared to the mainland. So we submitted this research to Ocean Science, and if you're interested in this, you can look at the DOI over here. And then we often get the question, do we also know where this litter comes from that we find in the Netherlands? That's what we wanted to figure out together with a bachelor student of ours, Bram van Duinen. So what he tried to answer is, can we find the probability that a certain location on this map is the source of plastics that we find on a beach in the Netherlands? In this case, the beach that we took in the Netherlands is here in the southwest of the Netherlands. So what Bram did is he released a lot of virtual plastic particles into the North Sea. And then he looked how these particles are transported back in time to estimate their origin regions. So this is called Lagrangian modeling. So in this case, we throw virtual particles into a virtual sea, and then we see how they are moved around by the ocean currents. Just to give you an illustration, in this case, we have the ocean currents which move from the west to the east. So if we would go back in time, we would see that most of these particles originate somewhere to the west of the Netherlands. So now you could say naively, maybe the plastics that we find on the beach here are originating from this red area over here. This is a bit too simplistic because you have to take into account maybe some of this red area is not the source of plastics in the first place. As you can imagine, we have more plastic input near coastlines, for example. And also we find that a lot of the plastics that we find in the Netherlands are coming from the fishing industry. So in this case, I drew this blue area where you might expect a lot of plastic input into the sea. Now what we want in the end is to combine this red area, so this area where particles are likely originating from that we find in the Netherlands, together with this area where particles are likely entering the water. So what we do is take this intersection between the two areas. So this area is basically both likely, it's the area where particles are likely to enter the water, but also beach in the Netherlands. So we considered three different sources for this project. First of all, we find that about 40% of the plastics in the Netherlands are likely originating from the fishing industry. So we see a lot of fishing nets lying around, so about 40%. And then we assume that about 50% slash 10% is either coming from the coastlines or from rivers. So in this picture, I illustrated where we expect a lot of plastic input.
If you look at the fishing intensity indicated in blue, we see that there's a lot of fishing industry going on in the English Channel, for example. So this could be a source of plastics that we find in the Netherlands. If you look at the coastlines, so that's the red areas, and the rivers, so those are the gray dots. We can expect a lot of plastic input from the Netherlands itself. As you can see, for example, we also have the Rhine in this area. And we can also expect plastic input from the coastlines from France, for example, or the UK. So Bram, he combined this map where we can expect plastic input together with his backtracking simulations. Then in the end, this is the average result that we obtained. So in this map, you can see the source probabilities of particles beaching in the Netherlands between 2015 and 2020. So as you can see, a lot of the fishing related items are expected to come from the English Channel. So we see a lot of expected plastic input over here. And a lot of the coastal and riverine input is first of all expected to come from the Netherlands itself. So we see quite high probabilities in the Netherlands, the Rhine, for example. We see the coastlines of France are likely origins of plastics in the Netherlands, and also the coastlines of the southeast of the UK. One major uncertainty in this framework is the amount of time the particles spent in the water, because if you find a certain object on the beach, it's really difficult to say whether it floated for 1 month or 1 year. So we looked a bit at the sensitivity of this. So in this case, I plotted the probability the particles originate from these areas when they have only floated for 1 month. So in that case, you see that particles are originating from quite close by, actually. And then if we play this animation, we can see what happens if particles float for a larger amount of times. So we see as the floating time increases, particle origins move more to the west, so more from the English Channel and even further away. And what's also really surprising is that when we increase this floating time even more, we also see that some of the particles are originating from, for example, Scotland, so near Edinburgh. So also this research was submitted. We submitted this to geophysical research letters. And if you want to look at the preprint, there's also a DOI you can look at. So now we've discussed basically 2 reservoirs of marine plastics. We've discussed that they can reside in the surface water, these garbage patches, and they can also reside on the coastlines. It's not the entire picture, of course. Plastics, they could also sink over time. So develop this biofilm, so this layer of algae on top of them. This makes the particles denser, eventually causing them to potentially sink down. We need to consider that particles might be mixed into the water column, influenced by the turbulence. We also need to consider that as particles age, they might experience fragmentation and weathering. And eventually, these particles might become so small that they are really difficult to measure. And to complete this entire picture, so to complete this mass balance picture, we also need to know what the likely sources of plastics are. So like I discussed before, are they mainly coming from the fishing industry, for example, from rivers, from coastlines? That's something we don't really know yet. So the big question is, how can we complete this picture? I would say there's 2 methods we could use. We could either use more observations. So the benefit of this is that they're really accurate. If you do your observations well, you really know what you measure. The downside of this is that they're very local, both in space and time, and they're often really expensive to carry out. So you need to go to the site where you want to measure. Costs a lot of ship time, a lot of man hours. On the other hand, we have models. These are clearly imperfect. There are a lot of assumptions that goes into the models, but they are really generalizable, which is the big benefit of this. So if you want to play around with a really simple model, we have this website, plasticadrift.org. And on this website, you can pick any location on the globe to see what would happen with plastics released at this location. So in this case, we picked the Netherlands to see what would happen with our plastics over here. And there you see that we expect a lot of these plastics to go towards the north, towards the Arctic. I think this nicely illustrates the generalizability of these models. So we can basically pick any location on the globe. And as long as we know something about the ocean currents, we can try to make predictions. And ideally, we would combine these generalizability of these models with the accuracy of observations. And that's what we try to do for the Mediterranean Sea. So we created a big Lagrangian model for the Mediterranean Sea. So basically, we throw virtual plastics into a virtual Mediterranean Sea. We allow these particles to sink down over time. So the colors of these particles indicates the probability that they are still afloat in this case. We also allow particles to beach. So in this animation, they light up in red when they end up on the coastline. And also in this model, we can play around with the different sources. So we can release more or less particles near rivers, for example, or near fishing related areas. So here you can see quite clearly, for example, how quite a lot of virtual plastics are released near the river Nile, for example. So here we have a schematic of the model. We assume there's 3 types of sources, just like for the project in the North Sea. We assume that particles might originate from the coastlines, from rivers, or from the fishing industry. And then we consider what we think are the 2 dominant sinks for plastics. So plastics can end up on coastlines, so beaching, and plastics can sink down over time. Now what we do is we basically treat this model as a function with some unknown parameters. So we have a rough idea of the sources of plastics, so rivers, coastal population, but we don't really know their relative importances, so how much is entering the oceans from rivers compared to coastal population. So what we do is we introduce 3 parameters, so these are the source strengths, and we can adjust these parameters a bit. So it's like a tuning knob, basically. Then also we assume that these particles are removed from the environment over time. So we introduce 2 time scales, I mean. We introduce a time scale for the beaching of plastics and a time scale for the sinking of plastics. And also here we have a rough idea of the time scales from laboratory studies, but we don't really know what the realistic values would be. And now in the end, the goal is to match this model to observational data that we get from the literature. So in this case, we gathered about 1,000 measurements in the Mediterranean Sea. So these are all measurements from the surface water obtained using these kind of nets. And now we try to tune these parameters such that the model output matches these observations as well as possible. So basically, we do a big model calibration. That's what we did. So we calibrated this Lagrangian model for the Mediterranean Sea. And then after calibrating it, we can look to see what happens with all the plastic that enters the oceans. So what we think, based on this calibrated model, is that about 50% of the particles will end up on the beaches, and about 50% of these particles will start sinking down. So that means a really small fraction actually remains afloat. In this map over here, we can see the areas where we expect most of the plastics to end up eventually. So we see, especially in the Mediterranean Sea in the west, we expect a lot of particles to sink down in the Adriatic. And if you look at the coastlines, we think that especially the southern coastlines are quite polluted, for example, here in the west and here in the southeast. What I think is really interesting about the study is that we also found that the plastic input into the Mediterranean Sea is probably quite a bit lower than was previously estimated. So we estimated input of about 2,500 tons, and it is much, much less than the previous estimate of more than 100,000 tons per year. And I really want to add here that this doesn't diminish the problem of plastic pollution. It just means that these particles remain longer in the environment than you would expect based on more input. So this model was relatively simplified. So we assume that these particles remain mainly at the surface of the ocean. Furthermore, no fragmentation was assumed in this model. But in the meantime, our team at the Utrecht University, so the TOPIAS team, tracking of plastics in our seas, we have been working on quite some projects to make the numerical models more realistic. So first of all, we have Delphine Lobel and Rein Fischer. They've been working on biofouling, for example. So like I said, over time, these plastic particles, they develop a biofilm on top of them. This makes them more heavy, eventually causing them to sink down. And what's hypothesized is that eventually they reach a certain depth where there's no more light. So what could happen is that these algae might start dying off. And this in turn could lead to these particles rising up again. So we see some kind of oscillatory behavior. And this is something we'd like to include in our models as well. Then we have Victor Oning. He has done some projects on the vertical mixing of plastics in the water column. So how do plastics mix into the water column induced by turbulence? We've released a study on fragmentation. So we published this fragmentation study in environmental research letters. So in this model, plastic particles, big plastic particles, fragment into smaller and smaller fragments over time. So we call this the cascading fragmentation model. It's also something we would like to include in future projects. And then finally, we also looked more in depth into beaching and resuspension. So this paper by Victor Oning and this North Sea paper that I just discussed. So also we would like to make these processes more realistic. And additionally, we'd also like to extend our analysis globally instead of just the Mediterranean Sea. So I'll show you some preliminary results. So yeah, please take into account this is really preliminary. What we did in this animation is we release particles at river mouths according to this model by Meijer et al. And then we calculate how this influences the plastic concentrations in the seas. So in the water, we get plastic concentrations in terms of kilograms per cubic meter. And in this model, we will also allow plastics to beach and resuspend back into the ocean again. So we also calculate the plastic concentration on the beaches in terms of kilogram per meter. So now we will run this animation. I think what's really cool to see here is how these garbage patches start appearing. So we really clearly see how this one in the South Atlantic starts appearing. We slowly see this one in the South Pacific appearing over here. And now we speed up the animation a bit. So now we see that about 2 decades have passed. We really clearly see these 2 garbage patches in the Northern Hemisphere. We see these 3 in the Southern Hemisphere, so the Pacific, Atlantic, and also the Indian Ocean. And according to this model by Meijer, there's a lot of expected plastic input in Southeast Asia. So that's also why we see quite high plastic concentrations in this area. And what I think is really nice about this model is that we can also play around with interactions between beaching, fragmentation, and resuspension of plastics. So in this case, I will show you what happens if we release some big plastic particles in the middle of the Atlantic. Now, over time, you will see that these particles start beaching, fragmenting, and resuspending back into the ocean. So let's take a look at this animation. These particles start spreading out through the ocean. And at some point, you will see that these particles have beached here in the Azores in this case. So in this model, we assume that plastics fragment mainly on beaches. So we assume fragmentation is dominant here, based on the fact that particles might experience more UV weathering, mechanical abrasion from sand and rocks, and oxidation on beaches compared to when they would spend time in the water. So we see that particles start fragmenting, so we get smaller and smaller fragments on the beaches over here. And now you will also see that these start resuspending back into the water. So it's really nice to see, I think, is that these beaches start acting as a source of secondary fragmented plastics. And if we run this animation for some time, we also see that these fragments eventually also accumulate in the garbage patches in the middle of the Atlantic. And like I said in the beginning, in the end, the goal is to create a 3-dimensional map of plastic pollution. So we also want to look what happens in the deeper layers of the ocean. So here we have the same idea. We have the particles sizes in the different columns again. So 6, 3, and 1 millimeters. But now the different rows, we have the upper part of the water column. So that's 0 to 5 meter depth.
and the lower part of the water column, so 5 to 15 meters depth in this case. Now again, we release a tracer in the middle of the Atlantic, some relatively big particles, and now we see how these start spreading out through the Atlantic. So in this case, we see they also start mixing towards the deeper layers. And this is especially the case for the smaller particles. So these smaller particles are less buoyant than the bigger particles. So you see a relatively large proportion of these smaller particles mix into the deeper water layer. So this is still very much work in progress, like I said. The next step is calibrating this model, which is still to be done. So the goal is, of course, to calibrate this model to as much data as possible. First of all, we want to calibrate the model against observations in surface water, just like for the Mediterranean project. So for the surface water, we have measurements both in terms of amounts per square kilometer and mass per square kilometer. Something which I think is also really important to take into account are particle size distributions. So in this case, we have the particle size on the x-axis and the amount of particles on the y-axis. So why is this important? First of all, it gives us an idea of which particle sizes contribute to most of the pollution. And secondly, what we found in our fragmentation paper is that this slope of this curve can also tell something about the fragmentation process. So how quickly are particles fragmenting? This influences the slope of these curves. Furthermore, next to these surface measurements, we would also like to extend the model with deep water measurements, so measurements from deeper in the water column. We would like to include measurements from marine sediments, if those are available, and also beaches. Finally, what's also really important, I think, to take into account is the litter composition. So this is here from Morales Casellas and co-workers. It's a bit difficult to interpret at first sight, but let's look at the open waters in this case. So the outer ring here represents the origin of plastics that we find in the open waters. So we see in open waters, we mainly find plastics which are coming from the oceans and waterways. So basically, this means most of the plastics we find in open waters are coming from the fishing industry, likely. And the small remainder of the plastics in the open waters are likely originating from the takeaway consumer category. And this is really different when you would look at the nearshore waters in this case, because in that case, we actually see that most of the plastics in the nearshore waters are likely originating from the consumer takeaway category. And the same goes if you would look at shorelines, where you also see mainly consumer takeaway plastics. Tips are really welcome. So if you have any large data sets, especially for marine sediments and beaches, we will be super happy to hear from you, because the more data, the better, the more accurate in the end our calibrated model will be. So it brings me to the conclusion already. So I discussed that data are generally accurate, but they're pretty local, both in space and time, and they are more expensive to obtain. And on the other hand, we have models which are clearly imperfect due to their many assumptions, but they're really generalizable, which is a big plus. And ideally, we want to combine these models with these observational data. So I showed you one example where we can relate the observational data to environmental variables. And after making a map from these variables to the observations, we can also use this map to make extrapolations to get an insight of where we expect most of the plastic pollution. And then I showed you some examples of model calibration. So we calibrated this model for the Mediterranean Sea using these surface measurements of plastic concentrations. And afterwards, we use this calibrated model to see where the plastic is ending up in the end. And please feel free to contact me if you have any tips or questions at my email over here. And thank you very much for listening.
Thank you, Michael, for a very, very interesting talk. Maybe we can, here we go. Maybe we can stop sharing your screen. You can stop sharing your screen.
Yeah.
If you don't mind, and we'll go through questions that our viewers have been asking on Slido, and I see already really interesting ones.
Okay.
And I will just go through them, and people can keep asking questions, and we'll go like this. Anyways, the first one is from Moam, and he or she asks if tides explain beaching likelihood. This could be useful for parameterizing beaching in global models. How well does it generalize beyond Netherlands?
That's a really good and difficult question. Yeah, that's exactly one of the reasons why I did this North Sea study. We want to know what kind of parameters are important for beaching to be able to use this information later on in our global model as well. It's really difficult to say how this generalizes for the entire globe, however, because in the Netherlands, we mainly have sandy beaches, while elsewhere on the planet, we might also have a lot of rocky beaches, for example, and there the beaching might be quite a bit different, actually. So yeah, it's a really good question. I think more data would be necessary to really say whether we can use our Dutch model to also extrapolate to the global case. So yeah, I think for now we have to keep our global model relatively simple, work with simple timescales. And if more information becomes available, where the tides also play an important role elsewhere, we can always include this later on. And I hope this answers your question.
Yeah, and I think I'm just going to jump quickly over one question that I had, is that the parameters that you evaluate, and are they only based on like hydrodynamical modeling data, or is it on observation as well? And have you tried doing like extracting virtual observation from the hydrodynamical model to try to train your model? Well, your AI model.
I don't really know if I entirely grasp your question. So are you talking about the machine learning part now?
Yeah, the machine learning part, yeah, sorry.
So for the machine learning project, basically all the variables that we introduce are all obtained from numerical model data.
Okay.
So we looked at the numerical model data. What are the tides at a given measurement location at a given time? The wind speeds, the currents, and so forth. These are all numerical model data.
Yeah, and then my question, did you try to do the same thing with observations?
No, we didn't, because generally these numerical model data are relatively accurate. They're also assimilated with observational data. Okay. So this means that your numerical model has been, they already tried to match the model with observational data that they have. So they should be relatively accurate. And also the data that we use is from the past. So people already checked whether this data is accurate regarding previous observations as well.
All right. Well, my question was more like, because it's lighter to use just observation rather than assimilated models. But let's move on to the next question. We have someone anonymous asking, have you looked at the effects of seasonality on the beaching of plastic in the Netherlands?
It's a really good question as well. Unfortunately, the data that we have is only from August. Because in August, that's when the beach cleanup tours were taking place. So that's also why the predictions that we made are only valid for August. So yeah, it will be super interesting to have more data for different seasons as well. But unfortunately, for the Netherlands, we don't have this data available. Yeah.
Okay, and I think that's really linked to the next question that we have. So since you have this bias in seasonality, someone is asking about the bias in tides. Because they say, given the 84,000 hours cleanup time, is there perhaps a skewness towards low tide during cleanup because of the accessibility of the beach?
Yeah, that's a really good question. That's also something we looked into. So we calculated what was the tidal height at the beginning of the cleanup tour and at the end of the cleanup tour. So this is also one of the variables that we fed into the machine learning algorithm. And there we indeed found that if during the cleanup tour there were higher tides, that generally less litter was found as well. So yeah, that's an excellent question. It's true. Yeah.
No, that's very good. Someone is also asking, how do you define a particle? Can you tell us a bit more about virtual particle characteristics in terms of windage, size, density?
So it depends a bit on the project. So for the Mediterranean Sea, we kept it relatively simple. So we assumed the particles were buoyant. So they basically reside at the sea surface, and they were influenced by the ocean currents and Stokes drift. So that's the influence from waves. Mm-hmm. And normally in these simulations, we assume that these particles are just below, they don't really stick out, which means that they're not directly influenced by the wind, for example. Mm-hmm. In the global project, we make it a bit more complex. So there we also consider different sized particles. So it also means that different sized particles are mixing in different ways into the water column. Also in that case, for example, the wave influence also changes in depth. So that's also something we want to take into account. So basically they're influenced by the ocean currents again, waves. And we're still thinking whether we should also do some simulations with some windage added for the really big particles. That's something we still need to explore, whether that's necessary.
Yeah, I think it's really interesting because even when I was doing research cruises, I could see that the first plastic garbage that we could see at the surface definitely had some windage because they're either like closed water bottles that are empty inside, so they have strong windage, or even those giant ghost nets. They have some kind of the structure at the surface is so different from water than that there is some windage. So it's definitely, but there are so many parameters, right? And as you were saying, you need to keep the global model simple enough to still kind of control it, of course.
Yeah, exactly. But yeah, you're right. For macroplastics, it might be important to have a look how important this windage might be. Yeah.
Mm-hmm. Yeah. So Noam is again asking another question. How interested are policymakers in your work? Are they interested in your results on marine attribution? She's saying, or he, sorry, for example, the debris accumulation in the Netherlands coming from the UK or from France.
Yeah, it's interesting. So like I said, we just published the preprint, so we didn't publish the real paper yet. So we didn't really have the opportunity yet to really present it to policymakers. But I would be really interested to see whether they're also interested in a research. Because I think this framework could also be applied to more vulnerable beaches, for example, where you have some vulnerable ecosystems. It would be really good to know at those locations where the plastic might originate from to really tackle it at the source. Yeah, I really hope they will be interested when we publish the final paper.
And as well, it could be really interesting in seeing like how policy on, like on certain products can alter the pollution. For instance, if the UK has a different policy than we have in Europe on fishermen dropping nets or things like this, or even on like products like consumers, products. Then if we see that, like most of the plastic that we see comes from Europe and not the UK or vice versa, then we can also have proof of some effective or non-effective policy. And I think that's really interesting to make that link.
Yeah, true.
I had another question that is going back to, I would say, the more physical part of the work. You're showing, and I thought that was really interesting, how islands and coasts become secondary sources for smaller fragments of plastic. And I was wondering in your model, if you took into consideration the different type of coasts, like beach or cliffs, rocks, mangroves. Is that part of your model, or the coast is just treated the same way all around?
Yeah, for now the coast is treated the same way. I'm also not sure whether a data set on that is available, like the percentage of rocky beaches versus sandy beaches. If anybody knows about this, it would be interesting. Let me know, because I think it would be good to take into account if possible. Yeah, but it would also mean that we need more data to calibrate them all again, because the more complex you make it, the more data you need to calibrate it in the end. But it would be really, really good to take into account, I think. Yeah.
Mm-hmm. All right. Next question from Carla. She's asking, why do you have considered water surface from 0 to 5 meter depth? Is it linked to homogeneous fate mechanism influencing the plastic and microplastics present?
For now, the choice is kind of arbitrary. So we use, I don't know if you're familiar with transition matrices. So we use a transition matrix approach where we divide the ocean into different cells. So we need to divide the ocean into different cells in depth. And so this was an arbitrary choice to use 0 to 5, 5 to 50, 50 to 500, and 500 and below. But it's a choice we can easily adjust in the end. The main important thing is that the measurements that we calibrate or model against should be somehow valid for the depths we look at. So if you look, if you use these net observations, they are usually obtained in the upper 50 centimeters, I think. So it would be good if the upper layer of the ocean also, if it's also resolved up to the 15 centimeter scale, such that these are at least are consistent. But this choice is kind of arbitrary. We can change it later on.
Yeah, it's kind of the same problem for every parameter we measure, right? If it's from satellite or from Argo, and we have this habit of dividing, as you were saying, the models vertically, and we always need to tweak it to represent something physical and not just the way we measure the ocean.
Yeah, exactly.
So I have one next question from Anonymous. So feel free if you listen to me to write up your name. I think it's really nice as well. How could regions around the world begin to use your model to assess sources of plastic on their coastlines?
So in principle, this framework that I presented for the North Sea, it can be extended to any region on the globe. And we also made sure that all the data that goes into this model is available globally. So for the sources in this framework, we used the fishing activity, which is available globally. We used riverine sources, also available globally. And we used this mismanaged waste near the coastlines, which is also available globally. And then all you need extra is these backtracking simulations. And you can also easily do that globally. So you can just download the ocean current data and then release particles at your beach of interest, basically. And by doing that, you can easily reproduce this method for any location on Earth.
Mm-hmm. So you don't have any plans of having an online cloud platform where people can just move around your model and look what kind of results they would get in different regions?
It's a super interesting question. It would be really nice to try it, actually. Because in principle, these sources, they are pretty, you can predefine them. I think in theory, you could also do the backtracking using a simplified approach, maybe using like a simplified transition matrix. So it would be super interesting to try to do this online on a cloud platform as well. But I personally don't think I have the time for that. But if anybody is really interested, hit me up.
All right, we can talk about it in the near future. Cool. Dan Wilson is asking, thanks for your interesting talk. What resolution flow fields do you use in global models? And what parameterization do you use for processes on a subgrid scale?
For the global model, the ocean currents are defined on 1/12 of a degree. And subscale process, that's a good question, because normally we add like random walk diffusion to our Lagrangian models. So that means that the particles can, they get like random displacements in space to model subgrid scale eddies, for example. So that's what we normally do in these Lagrangian models. For the global model, however, we use a transition matrix approach. This basically means we divide the globe into approximately 1 by 1 degree bins. And then we calculate the probability that the particle moves from one bin to another bin. And during this binning process, you already introduce quite a bit of artificial diffusion. So that's why we decided for the global model not to introduce extra subgrid scale diffusion. Because it's already in there, basically.
from the transition matrix approach. I hope that answers your question.
Well, it was Dan's, so I hope it answers Dan's question. Feel free, Dan, to write up a follow-up question if that was not complete for you. And then we have Carl Nettleton asking, if the sources of plastic collecting can be identified, solution can be implemented. How can your model be used for by local folks working on plastic issues?
Yeah, so we already discussed that in principle, this first framework I presented is universally applicable. So yeah, if it would be possible to further simplify it and run it online, I think it will be yeah, really great for local communities as well, because then they can really see where the plastic is coming from and maybe try to address these issues at the source. Furthermore, I think also this machine learning framework will be applied to other locations. All you need is a consistent set of measurements and some environmental variables, for example, the weather conditions. You can then try to make this fit as well, try to make this map from the weather to the amount of plastic that's found. And if you have this map for a certain location, you can also look for what kind of days do we expect most plastic pollution. And then you can tackle this problem by really going to the beach when you expect a lot of stuff to actually end up on the beach. That would be a possibility. Yeah.
Mm-hmm. So basically, there are, if I understand correctly, there are two ways. One is tracking the main sources, going backwards in time from observation, and maybe isolate a port or in urban areas that flow, like create a lot of pollution. Or you can look forward in time in the future with predictions and guide cleaning activities, right?
Yeah, exactly. Yeah.
Oh, that's great. Okay. Carl is saying that is probably working at Open Oceans Global, and they have developed a model that is looking at backtracking plastic online using current information and preparing to incorporate tidal and wind data. So maybe that could be the way for a great collaboration there.
Okay.
On the more technical side, I would say someone is asking, have you tried to do a correlation matrix before you create your machine learning model? What kind of validation do you use?
Good questions. So indeed, we looked at the correlation between different variables. So I didn't really want to go too much in depth for this project because it's really technical in the end. But what we did is we looked, we have a really large set of explanatory variables. Then we binned these variables in certain clusters by looking at their correlations. And then we let the machine learning algorithm pick from each of these clusters the best variable, so the variable which gave the most predictive power to the model, basically. So indeed, we looked at the correlation matrices. And then the second question was how we validated the model. So what we used was 5-fold cross-validation. I don't know if you're familiar with that, but we split the entire data set into 5 parts. Then we use 4/5 to train a model and then 1/5 to validate this model. And then we repeat this 5 times over. So this time, so by doing this, we can also look at the final correlation between the model and observations. And this was actually quite nice. We saw a Pearson R of, what was it, 0.7 to about 0.8. So we were really happy with the performance of this model.
Yeah, you can be. Dan is actually saying that the earlier your answer to the earlier question did answer his question. So he's saying thank you for the explanation. We have Florence Cutat, who was asking for the sinking plastic. You mentioned that biofouling is growing on the particle. How do you implement that into your Lagrangian model?
So yeah, if you want to look at the exact details, we use the same model as Delphine Lobel and Reint Fischer used in their paper. So what we do is we look at the primary productivity fields, for example, to predict how much algae will grow on top of the plastics. Then what else did we use? So yeah, we used primary productivity fields. We used fields for the zooplankton, the phytoplankton. So yeah, a lot of biochemistry fields are going into this model to model how quickly this biofilm grows in differently sized particles, and to predict how quickly they will sink eventually. Yeah.
All right, thank you. I think that's the last question I had in it was a list of 17 questions, so it felt like I was cooking you or something.
That's great.
So thank you for your for your insight and answering all these questions. I think it was really interesting. If there is one last question, you guys from watching us can drop it. Otherwise, I'm going to thank Michael again for giving us this presentation, because I think that's linking modeling and observations and all kind of modeling, the Lagrangian, the hydrodynamics, the machine learning, all these kind of modelings are really important, and they're definitely I believe a key element to monitoring and understanding, and of course addressing the marine litter situation in our oceans. So thank you again, Michael.
Thanks a lot for the invitation.
Yeah, of course. If anyone wants to, get Michael's contact or ask him question, you can either, I guess, find his email address online, or if you can't, you just send us an email to the OPW people, and we'll be happy to forward your questions to Michael. And thank you all for watching us today. I think it was really exciting. This is our last webinar of the season of 2021. We'll see you again in January 2022 for a new series of webinars on ocean plastic. Let us know if you have any comments, if you want to participate, if you want to be one of the speakers. We'll be happy to have you. Of course, we're looking at trying to have the best inclusion in terms of diversity and age and everything. So we'll be happy to have anyone with us on the ocean plastic webinars. So thank you again to all of you. Happy New Year, and we will